All right, so first of all, thanks everyone for making it at 9 a.m. That's a challenge for some people, so thank you very much. Like Jake said, my name is Phil Russell. I'm going to be talking about essentially a caching scheme that's implemented in Intuit's kind of custom GraphQL orchestrator. And a bit about me, so I'm a staff software engineer at Intuit. I work in services, APIs, infrastructure. As far as stuff that I like, it's compilers, language API frameworks, and distributed systems. So it turns out that GraphQL is actually a really good kind of center point for all of those, right? Okay, so what are we going to be talking about today? We're going to be talking about GraphQL and Intuit. Specifically, we're going to be talking about, like I said, a caching scheme that kind of supports our larger scale use cases. We're going to be talking about control mechanisms for that cache, and then we're going to be talking a little bit about eventing and caches and kind of some of the challenges therein, right? So, section 1. Okay, so what goes on at Intuit? Well, one of the things that when you kind of search around for GraphQL, especially on the tutorials and things like that, you kind of end up with like, I have my schema, I have 20 types, I have like 4 services that I talk to, and everything's nice and well formulated, and you can actually like trace the traffic through that entire example, right? Doesn't really work that way at Intuit. So we have 1,800 addressable entities. We have 10,000 expanded types, along like the connections and edges and things like that. We have over 1 billion requests per day, 100 product teams, 1,000 different services. So we kind of get into this problem of, well, I want to go and build, some great new product, and we have these tons and tons of services that do great things. How do I actually go and tie them all together, right, in kind of a sane way, right? And that's where GraphQL kind of enters the picture. So this is your classic GraphQL gateway picture, and like I said, really what goes on is we have, for the past few years, we've been running a custom GraphQL gateway, and then I'm going to go and talk basically about the caching layer in a little bit, but I just want to make sure that everyone's kind of on the same page about what a good first step looks like, right? So we basically just have a request come in, we go to the gateway basically figures out, here's type X, it goes to service Y, and this goes on for however many services that you want to tie together from your query, right? So if you're familiar at all with, Apollo Gateway or how that works, if you've seen that, then same idea, right? And yes, it does say REST service. I'm not going to talk about that part. Okay. So problems at scale, right? So again, this goes back to, oh, they got rid of my, whatever. That's fine. I had a nice little emoji right in the middle that kind of looked cool, and then for some reason Google Docs decided to get rid of that. So what can you do? Okay, so assume you have like 100 different services, right? And then assuming some access control, you're some client, you go and make a query, you can go hit all 100 of them, right? So again, if we go back to our previous slide, that's going to go and funnel through this GraphQL gateway. So you can imagine, you get like 1 million different queries doing all this, bad things can happen. So specifically, bad things, n+1. So if you're not familiar with that, basically what it means is that every single type in your query shards off to a different service, right? And then you have problems, because at that point, it just basically becomes, it's sort of like how stampeding cache kind of works, but for services, where they just keep rotating around and around and around across your different services. Everything goes down. This has happened, right? I've been in the calls. So it is definitely a real thing, right? So solution 1, how do you kind of mitigate these things, right? So solution 1 is, well, you basically do graph compaction on the different types, and you say, let's collate all the common subfields or subcomponents to the same service that we know will map to that, right? So if you haven't really seen that, basically it means, you can kind of regard it as everything inside of a GraphQL request as a tree. So you say, this portion is going to go to this service, this portion is going to this service. So you basically compact along those lines, right? Solution 2, cache everything, right? It's kind of a brute force solution, but actually it works pretty well in practice, right? So mitigate effects of n+1. So kind of our first stab at that kind of ends up looking like this, right? Where we say, here, let's just cache at the service level, right? All's well. Well, but there's still problems. Because this works if you have 3 different services going downstream. Doesn't really tend to work so hot if you have 100, right? So, and we'll get why. So again, 100 different services, 100 different caching layers. At Intuit Scale specifically, that causes a lot of developer friction because we allow you to create services, right? We say, here's this automated pattern to go create different services. Well, by the way, if you want to go and plug in our GraphQL, orchestrators, then you got to go and set up your own caching layer. Well, that turns out to be kind of a high friction barrier that a lot of teams don't want to deal with. There's no way to coordinate any of this, right? So you're just going to have duplicate data floating around in different caches. There's basically going to have, one copy from a minute over here and one copy of it from 30 seconds over here. How do you reconcile all this? It gets in, because at that point there's no source of truth except for going down to the data provider again. At that point, why are you really caching in this way anyway, right? So how to solve cache at the edge, kind of the point of this talk, or at least my title. But really you should kind of think of this as, let's go and try to get a common data layer, or at least a common L1 cache, right? So that's what light blue is here. So if we go back to how, basically caching, L1, L2 cache works inside of OSs. So we can kind of think of this caching layer for everyone as kind of our L1, and then basically the service-specific caches are L2s, right? So in this picture, we haven't gotten rid of the service-specific caches, but we are pushing a common data layer over to the gateway, and that's basically the source of truth for most of the system, right? So if a client, basically if you're just another downstream service and you want to say, I want to set up, you don't have to go and build another cache if you don't want to. You can basically just cache at the edge, in this case, the edge being the gateway, right? So, and another point, if you add intrinsic functions inside of this light blue, if you know what those are, you have a data grid. Poor man's version anyway. Okay, so caching at the edge, right? So basically this kind of covers what I already went through, but we're going to lead into some other things. So basically our request response caching just isn't really good enough. So for example, let's say that query 1 goes off to 1 and 2, query 2 goes off to services 1 and 3. We're going to get a lot of duplicate data evening inside of the common caching tier, right? Which does matter at scale when you're making a billion requests over a day, because basically you're just going to fill up your entire memory buffers, right? So we want to ask, is there a way to store and find common components? And that's kind of what we're going to cover in the next big section, which is overlapping response caching, right? Okay. So basic idea, how does this really work, right? So I'm going to use the Star Wars API as a motivating example, and then I'm going to enhance it later on in a much nicer way. So anyway. Let's kind of look at these two queries, right? So we have one query that comes in. It basically asks for, some set of character information. We have another query that comes in that asks for essentially the same or a subset of that character information, right? And basically, if we just did this naive request response caching, we would basically create duplicate entries everywhere, right? So what we want instead is to say, hey, look, this component is the same across everything. I just want to pull that data, right, from the cache for this component and insert it into my response for query 2, right, or however many queries this goes along, right? Well, that sounds great, but whenever we go and cache stuff, we need to have keys, and we need to be able to do an apples-to-apples comparison to actually go and figure all this out, right? So how do we do that? Basically, an object ID, right? This has kind of two core properties, which is that it is the same across requests for whatever's basically object inside of the request graph, and it needs to be globally unique ID across the entire system. So what does that mean? Basically, it means that if you go and if I go and ask for some character with this name, and you ask for the same guy, it's going to have the same object ID, right? So that way that we can actually know I'm going to map this character, and it's going to be the same inside of the cache. So the actual formula is basically this. It's basically a hash of a domain, a type, and essentially a local object ID. Domain is basically just a set of types. You can kind of think of it as, the Star Wars API / characters is, Star Wars API is a domain, right? And then inside of that, characters is a type. So there you go. Okay, so conceptually speaking, not actually really, but conceptually speaking, this is kind of what goes on, right? So Basically, angling down on the left is query 1, and angling down on the right is query 2. We can kind of split this up into a bunch of different subcomponents and essentially assign keys. How do we do that? We basically parse the different queries into their AST form, and then we basically use a visitor to go and decorate everything. Right? We compute it using that hash function, or sorry, not hash function, object ID assignment function that I basically covered in the previous slide. Right? The other thing that's very important, you got to store each of these things inside of a runtime table. Like I said, we run our own custom orchestrator, so we can do that sort of thing. I don't know if any of the Apollo server does that, but anyway. So, point is that we have a common component here at the very bottom in dark blue, same key, right? Apples to apples comparisons. That's very important later. Okay, so I'm gonna kind of go through this quickly, but this is essentially the entire flow across the different queries, right? So I go and make, a query for basically what we talked about here, angling down. Let's say I ask for all the characters in A New Hope. Basically, we go and parse things. We assign the object IDs. We do a lookup. We get a cache miss, right? There's nothing in there. We can't find it. So we go to the character service, and then we go and store the characters in the queries. Oh, sorry. We store the information plus the original query that it originated from, which will become very important later. Okay, that's great. So now query 2 comes in. We basically say, I want some of the characters or a character from A New Hope. We do this exact same thing as in the first query. And at this point, we get a hit because some subset of the information, or it's actually a superset of the information that we're asking for, is inside cache, right? And critically, which we'll cover in gory detail, this can either be by primary key or secondary key, right? Okay. So how do direct lookups work? So a direct lookup is basically you're asking for, in this case, let's say a person from the Star Wars API, and you're basically just saying, your object ID is this, right? So it's just a direct reference, right? This is pretty easy as far as how it works in the cache. It's just essentially a key value set right there. So if you're backing this one cache D, it's just set key value, right? Pretty simple. So this works for the single object case. But, those are really simple, kind of boring queries, right? It's like, get me one thing. Well, that's great, but, we want, actual queries. Like, let's chain things together into a tree. Let's go and, ask for everything that belongs to something else. Let's filter, right? And again, this is the primary key case. It's kind of visualized. So, we go and basically map, Han Solo and Darth Vader to these IDs. The other point that is good to keep in mind about this is that these form kind of a leaf node in the graph and cache concept, which I'll cover in a little bit. Okay, more complicated queries. This is things I actually care about, right? So like I said, we never really ask for here, just give me this guy, right? We ask about, I have this film, give me all the characters, give me their homeworlds, give me this, give me that, right? We basically want compound connections, right? And if you kind of go through this, there's really only kind of 4 cases that can cover, 3 additional cases that can cover all of this, where we say, I want to select, some information by a foreign key. In this case, we'll say, parent key, which is kind of a pointer up in the tree. I want to select, where my ID is in the set, or I want to set where another foreign key is in a set, right? It may not be too obvious just kind of looking at it from left to right, but if you actually go and parse the semantics of how these things work behind the scenes, they kind of map onto those cases. And it turns out that's actually a really good thing because that sets us up for how secondary keys work, right? Other point, parent key is the kind of like I said, it's the pointer to the parent in the graph, which will become very important in a little bit. Okay, so we're going to start our secondary keys. And just a review, primary keys, easy, set key value. Secondary keys are where the magic happens because they allow us to essentially store trees in memory, right? So our cases are, essentially equals foreign key in a foreign key set, in a primary key set, and we can cover them all using this kind of the same notation or the same secondary key function, right? So secondary key is computed as a hash of the type of the sub or the thing you're looking at, in this case character, the actual field name, in this case would be, parent key, And then the field value, which is basically the, in this case, would be going A, B, C, D for A New Hope or something like that, right? So then this kind of gives the semantics of that. So kind of ignoring that part, how does this actually end up looking inside of the cache? Well, we see that on the right because we can see we stored the film object itself keyed to A, B, C, D. That was just a direct assignment, right? And then we go in, and then on top of that, besides these kind of low-level objects with Luke Skywalker a character and Darth Vader's a character, we also have this secondary key set right here, and that's pointing to two other IDs, right? So that's basically how things all tie together, because at that point we can say, okay, well, if we can compute later that you map onto this secondary key, then we can go and pull your IDs from cache and find your entry, right? So we'll go into an example of that. So query 1, I select characters where my parent key equals A, B, C, D, A New Hope, something like that. So we get a cache miss, but the data response is basically like this, right? So it's just some kind of JSON here. We have Luke Skywalker, we have Darth Vader, here's their object IDs. Critically, here's their parent key, right? So basically, we do this automatically inside of an SDK, where we just say always return parent key to support this. And then at that point, I can create those 3 entries, right? I can say, here's Luke Skywalker, 1, 2, 3, 4. Here's Darth Vader, 5, 6, 7, 8. And then I can compute the secondary key set and map those 2 keys inside of it, right? So at that point, what I can say is, here's query 2. Select from characters where his object ID is this, right? So that's Luke Skywalker. I can get, select where it's Darth Vader. I get a hit, I get a hit. I can select where the object ID is in either of those. I can ask for sets now, right? And then I can also say, select where characters where their parent key equals A New Hope. I get a hit, right? So this is basically what really makes it all work, is the fact that you can ask for several different versions of the information, subsets, and it's all there, right? So, okay, so how does that look like? So this is where it gets fun. So I don't really like the Star Wars API as like a talking point, because I feel it's like a little contrived. I mean, it's nice. So we're going to go ahead and extend it, and we're going to do it with something that Intuit actually deals with, which is credit reports for Turbo. So we have Apollo Federation now. We have Apollo Gateway. We can bolt on extra fields. So imagine there's some new, some extended Star Wars API schema with credit reports for the characters, right? So a little dorky, but whatever. And then as our architect kind of put it, well, maybe it's their midichlorian count, right? Something like that. And the point is, because this was an actual motivating engineering problem, which is that to get credit reports, you should go to TransUnion, Experian, whoever. And the point is that it's a third-party service. Round trip can take a long time, 15 seconds more, and it doesn't really change that often. It only changes like once a month. So what's the point of kind of doing it every single time that someone asks for the credit report? Well, there isn't. Right? So instead what we'd like to do is just get it, go and cache it for a long time, and save the cost in terms of latency and everything else, right? So in our contrived example of this, we say, here, let's have the credit reports for Owen and Baru, and then we're going to basically build what that looks like inside of the object cache, right? And you can conceptually just see it as a 2-tier tree, and then everything that has a primary key, which is a direct object ID, is stored inside of the table. So Owen has PK1, Baru has PK2, those are characters, and then PKs 3 through 6 are credit reports, right, for them, right? And then basically there's actually 3 different secondary key sets held here. So we have basically between, so PK1 and PK2 are in the first one, and then the rest are in the others, right? The point is that what it's really doing is it's kind of storing the entire or request graph inside of the cache, right, across different queries, right? And at this point, we can basically start doing stuff like what I kind of showed a little earlier, which is I can start making several different versions of the same queries and ask for the different sub-pieces of the data, and it's all there, right? So, okay, comparing queries across requests. So how does this work? So going back to Star Wars API, vanilla version. So we ask for our kind of like our big chunk of data, right? We say for New Hope, I want planets and characters and whatever. And then basically we just ask for, I just want the characters, right? So at this point, what we can determine is, at this point, after having shown with the structure that I showed you previously, and storing the original query that originated that structure, very important point, we can do basically set comparisons, right? So if you take all these fields and you basically just say, you know what, I don't really care about objects, I just care about film.planetConnection.total count, film.characterConnection.characters.name. You basically just look at them kind of like as strings, really, right? And it works fine because it's basically just a canonicalized mapping of all these different things. So you say, okay, fine, you asked for this set of information. Over here, you asked for this set of information. Is what you're asking for over here a subset of this? Well, then it's safe to return, right? So again, we have to store the original query for this to actually work. And then we really get a lot of cache, increased cache utilization from this, right? Because you can ask for any combination of the information from the stored query inside of other queries, right? And this can go as long as it's held in the cache by its TTL. So now another point is, so let's say you ask for a superset instead, right? I guess we're talking about subsets. Well, superset actually goes and says, well, it's not safe to go and return data, so I'm going to go down to the downstream service, get that superset of data, and then remap all the entries, right? So at that point, it's basically whoever's asking for the most information wins, right? So, and then another sticking point. So if you're asking for additional input variables, well, basically you kind of have to do the same thing that you did with fields. You have to sort them, you have to canonicalize them, store them alongside with the original query, and then basically do this additional sub-comparison across the input variables. Because again, we have to say you can only return stored data if it's safe to do so, and you can't really say, well, if you asked for, it's basically function comparisons, right? If I went and asked for, some permutation of the input, and you ask for another one, and we sort them and they're not the same thing, well, then it's not safe to return data from those two, right? So, okay, so that's the scheme, right? And now we're going to talk about how this works across an entire system, right? So basically, we have some additional kind of mechanisms for making sure that different data services and clients have control over whether they really want things cached or not, right? So basically, we just use cache control. So basically, if you're the client, you can say, I don't want things cached. This actually happens in our credit report example because a lot of the time, what different services end up doing is saying, you know what, yeah, the data's in the cache, but I just want to make sure, randomly that this is the latest and greatest. So I'm just going to, basically flip a coin and go and get the latest and greatest data, right? And then if you're a data service provider, you can say, I don't want this data stored, or I want it stored for, this amount of time. And then 0 kind of, ends up getting abused as like evict from cache. Because if you actually go and look at the cache control spec, there's not really an evict mechanism. So, you can do that. OK, so this is kind of like future state. This actually isn't really a thing yet. I just want to touch upon this because it's kind of important when you're talking about caching and especially data consistency in a large system. So really what we've been talking about so far is kind of request response caching, right? So we basically made a bunch of different requests across different queries. We went and set up our scheme. And then we can basically say, I as a service provider can either evict or set or whatever. Great. Well, really what we would like to do is say, you know what, forget this, because that basically happens all over here in terms of requests. What I'd really like to do is say, I'm a data provider, I have events, I'm going to put them on a bus, and then I want that put up on the caching tier, right? And then that really turns it more and more into this kind of data grid concept, right? So, this kind of brings up a lot of problems because you could have tons and tons and tons of events, actually more. You can have more events than you can have requests. in a lot of different cases, right? Because data changes, a lot in certain services. So how do you really deal with that? And again, this is kind of future, like we were kind of figuring this out. But essentially, you can kind of get into this notion of, you got to support basically standard interfaces across the stack. And really, at that point, the kind of sane way to do that is to use code gen, right? You basically have to say the interfaces for data ingestion, the interfaces for at every tier, essentially, both the API layer, data lake, whatever. If they're the same, then you kind of avoid a lot of problems, right? And then the other thing is we basically get in this notion of kind of data snapshots, where we say, yes, you had all these different events, and they did all these different transforms, but we can basically aggregate what that looks like within a snapshot of 10 milliseconds or so, and then basically that's what gets pushed to the data tier, right? So you may not really be getting the latest and greatest, but you'll get good enough for your purposes inside of the data tier, and then you can always essentially set up your mechanisms for people to bypass that, right? Okay, so let's sum up main points, right? So basically, this is about object IDs that are being used for this comparison across different requests. Basically, a primary key selection is very easy. It's basically just a hash table get. And then if we want to do something more complicated, like an actual query where we say, let's go check against a foreign key, or let's use in clauses, then we have to construct these secondary key sets, right? So really what this forms, like I said, is an in-cache shadow graph comprising of all the different relationships of the levels of the tree. And then common components can be served from the cache. And essentially we say we're going to compact everything inside of the graph in the cache. And then basically we use subset comparisons to go and compare different queries. So there you go.
Thank you, Phil. Thank you, Phil.
Yeah.
I think it takes a lot of work and a lot of preparation to talk about something as hard as cache. So it's really cool. It's really cool the work you've done, especially the visitor pattern. Traversing through the AST for object IDs is both really clever and really good use of the visitor pattern. So that's great.
So I'll also be hosting or co-hosting a roundtable at noon on caching. So if any got any questions or anything like that, just come ask.
Yeah, come see him at lunch.
Yep.
Thanks, Phil.
Yep.
So up next, also just as a quick note, we are running a couple minutes behind in this room on purpose, just because it takes a lot of time to get back and forth between the rooms in the building. So if you're coming to this room, we are starting a couple minutes late, we do know. Up next, we have somebody here to talk about another deep dive. We're talking about Kotlin and how GraphQL and Kotlin can work together. He's an architect at PayPal. He codes in 7 languages, I'm assuming one of which is Kotlin, considering you're talking about it. And he's been a software engineer for almost half of his life. I think the exact number was 42% of his life? 42.93? Very, very precise. But yeah, 42.93% of his life, he has been a software engineer. And I hope you enjoy his talk. Give a round of applause for Rohit.
Yay! Happy Halloween, folks. Everybody's so serious today. I couldn't find my wife's lipstick, otherwise I would have that thing done.